this lesson, we'll start learning about stoichiometry. It's a big word, but it basically just means any of the math and chemistry that requires a balanced chemical equation. In this lesson, we'll begin by learning how to do mole-to-mole conversions, and then branch out to learn how to do mass-to-mass conversions. All right, just to remind you, the homework yesterday was to calculate the molar masses of all the chemicals used and produced in the lab that we did yesterday, okay? And I gave you a definition. It's a pretty simple definition. Molar mass is the sum of all the average atomic masses of all the atoms in a chemical formula written in units of grams. So 1 mole of a compound is equal to this mass. So it's just an addition problem, guys. And I know you guys can all add. All right, average atomic masses are found on the periodic table of elements. And in the lab that we did, we reacted lead nitrate with potassium iodide. And I'm purposefully leaving off the physical states and the balance of the equation. I'm just writing down the formulas for now, because it's all we need for the homework. You don't need to have the coefficients that go in front of these numbers, and you don't need to know the physical states that we usually put after the symbol of the compounds to do molar mass. And when we put these together, we produce lead iodide. This is a double replacement reaction, so lead goes with iodine, which is a negative ion, so we call it iodide. And then we get potassium nitrate. Okay? So you have to calculate, for this homework, all of the molar masses for all 4 of these compounds. Now, and it's not hard. It's just addition, really. Okay? I'm going to, just for the sake of some clarity here, do it on a spreadsheet. Okay? What? I know, really. Come on. All right. So, the atomic mass of lead is 207.2. Okay? Yes? What's the atomic mass for nitrogen? You don't know? What? Oh, thank you. You're right. I put an extra period in there I don't need. Okay. How many nitrogens are in the formula, guys? How many nitrogens in this formula up here? 2 nitrogens. So we need this twice. And what is the atomic mass of oxygen?
15.9994.
Okay, that's a good point. Let me point something out to you. Let's go back to the camera here and look at this. Okay. Excuse me. We're not going to count it against you, but that exponent right there, that's not really an exponent. That refers you to this right here. Well, let's see, 4, that's 6 right there. Refers you to this right here. Okay? And all this is saying is that oxygen's atomic mass is actually somewhere between here and here. It's not this actual number. Okay, so that you don't use that little superscript number right there. All right, you got to watch out for what that means. It's not a number you're actually using. And what it means is that depending on where you are and what you're looking at, the average atomic mass can be different for oxygen because the different number of the isotopes are different. In fact, one of the ways that we can tell that somebody has taken, let's see, what are they called? Steroids. You know, illegal steroids, the kind you build muscles with, right? Is that everybody has steroids. You have steroids in your body, okay? But human steroids, your body self-selects certain isotopes of carbon, all right? It prefers certain isotopes of carbon. So if we do a test of the steroids in your body, we should find a certain percentage of certain isotopes in your body that are the type that your body selects. Man-made steroids don't make that selection. So we can tell that you take a man-made steroids by the percentage of isotopes of carbon in your steroids. So that's what that number's for anyway. Okay, so we're really just looking for 15.9994. Okay. Oxygen has an average atomic mass of 15.9994, but we have how many oxygens in the formula? 6. So I got this 2. Whoop, there, wait a minute. I'll get to it in a minute. copy, paste, 2, 3, 4, 5, and 6. And we need to add all those up. So what we need down here is the sum of everything that we had before that. So all this right here gets added up together. All right, and we get that number right there. Okay? That's the sum of the atomic masses. All right? So the average atomic mass, or the molar mass then of lead nitrate is 331.2098. That's the unrounded answer. How many significant digits do I need to have in this answer?
4.
4, because after this 2, when we're adding everything up, I taught you in here you're supposed to line all your numbers up vertically, and any empty slots to the right, those resulting digits get rounded off. So after the 0.2, everything gets rounded off. Okay? So we're going to round it off from here. And we get 331.2 grams. That's the molar mass of lead to nitrate. To get full credit for this, the person who's doing this work has to have justified work to show it. Okay? So they either have to show, as I did in this spreadsheet, they've added all these numbers together, or they could do it by multiplication. Okay? Let me show you what that might look like. Well, I'll tell you what, I'll do it. I'll use the spreadsheet to help out, but I'll show you here. You also can do this. You can say 207.2 times 1, 207.2, and then 14.0067 times 2. So the sum of all the masses of the nitrogen is 28.0134, and oxygen's atomic mass is 15.9994, and there's 6 of those, so you could do this. And 15.9994 times 6, 95.9964. And then you add all those up, you're going to get the same number. And you round it off. Okay. So either way, they have to have one of the two of these things to get credit for it. Okay? They either have to have all these numbers added together to show credit. 1, 2, 3, 4, 5, 6, 7, 8, 9. The answer, and the rounded answer is 10. Okay? Or they're going to have this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, guess what? You get 10 points either way. All right? Anything they're missing, you count off a point. So we're going to make this molar mass, all these molar masses worth 10 points. Okay? Got it?
What if we have just the answer?
Huh? Then they haven't justified their answer, have they? They could have looked that up somewhere and said that was their answer, but they haven't justified they've done the work. They can ask for makeup too. So no, if all they show is the answer, it's 1 point. Okay? All right. Say what? Oh well, sorry. All right, so the second chemical formula is going to be potassium iodide. Potassium has an atomic mass, or an average atomic mass. Let me get rid of this spreadsheet for a minute. An average atomic mass of 39.0983. 39.0983, right? Okay, and then iodine has an atomic mass of 126.90447. 126.90447. And we get an unrounded answer of 166.00277. And then we got to have 4 digits after the decimal. 1, 2, 3, 4. You're going to underline this digit here. That last 7 there. And your answer should be 166.0028 grams. Okay? Again, that's 10 points if they show all their work. If they don't show any work, okay, they don't show any work, they only get 1 point. They just show an answer. All right? All right, lead iodide, well, that's 1 lead. And it has a mass of 207.2. And then we have iodine, so there's 2 of those. 126.90447, 90447. And I get 461.00894. All but the first digit after the decimal get rounded off. And so we get an answer that's 461.0 grams. Okay, that's the molar mass for that. Again, 10 points. Okay. Potassium nitrate. Let's see. Potassium we said was 39.0983. Nitrogen is 14.0067, and oxygen 15.9996. Oh, I'm sorry, 9994 times 3 in this case, and we get 101.1032. And, oh, there's no rounding off to be done on this one because there's no empty slots to the right. Okay? So we're still going to give it 10 points here. All right, so 40 points for everything if they do everything correctly. Okay? You just got to have the right answer, show the rounding, and justify your answer through the math. You have to do the math on the paper someplace, and it has to be reasonable math. Write down this problem. And this is where we're going to start learning about stoichiometry. All right, now we're going to get back. That molar mass you calculated is going to be part of it today. But for right now, this is the basis we're going to start with, the basics we're going to start with for learning stoichiometry. Just write the problem down. I'll show you what we do. Okay, guys, now this problem, this statement here, implies an equation. At this point, we've had units of instruction where you learn to write formulas. You've had units of instruction where you learn to write equations, predict the products of equations, and balance equations. So right now, you should have all that you need in your toolbox to write and balance this equation. You need that first. Okay? So everybody should write and balance this equation first. All right, let's see. What we're going to start then with is methane. And guys, we learned this in a previous unit. Methane means you have 1 carbon, and all carbons have 4 electrons, and so they need 4 bonds to have a full valence level, and you get CH4. For us, in our super simplified way of thinking about physical states for hydrocarbons, if the hydrocarbon has up to and including 5 carbons, we're going to call that a gas. We're going to say that oxygen is always a gas. And when we combust something, or we have a hydrocarbon reacting with oxygen in combustion, we're always going to produce the same 2 products, carbon dioxide as a gas, and water. And because of the heat what you get when you burn something, water is going to be steam or a gas. Okay? Now, then all we have to do is to balance the equation. So we're going to list all of our elements in the formula or in the equation. And we're going to build our atom inventory grid here. Count everything up. I currently have 1 carbon and 4 hydrogens and 2 oxygens on the left. And on the right, I've got 1 carbon and 2 hydrogens, and 2 plus 1 are 3 hydrogens. Okay? What I need to do is to get the same number of atoms of each species on both sides. Okay, I need to have them equal on this side and this side, or this side equal to this side. Okay, so that we don't violate the law of conservation of matter, because we need to have the same number of atoms on both sides. Now, since I have, what we always want to do is to save oxygen for last. Hydrogen next to last, but carbon's already balanced, so we're going to start with hydrogen because carbon's already balanced. To get 4 hydrogens on the right, we'll need a coefficient of 2 here. That's going to multiply that 2 hydrogens in the formula by 2, and we're going to get 4 hydrogens from that. Now, the oxygens are in 2 places on the right. I've got 2 oxygens here. Over here I've got 1 oxygen, but this 2 also multiplies that 1. So we've got 2 oxygens here and 2 here. And 2 plus 2, 2 plus 2 equals 4. So now we have 4 oxygens. So to get 4 oxygens now on the left, I just need a coefficient in front of this of 2, and 2 times 2 is 4, and everything's balanced. Okay, so let's go back now to the problem and discuss what we're going to be able to do with this. All right, so what we're starting with is 15.75 moles of methane. Okay, now in Unit 1, I taught you what's called dimensional analysis. Okay, we're going to use that dimensional analysis to solve stoichiometry problems. Okay, so we got 2 different kinds of problems here, but they're really kind of the same thing. Dimensional analysis is how you set it up. Stoichiometry is what it is because we're going to be changing from one chemical species to another, and for that we need moles. Okay? So, stoichiometry, the definition that I want you to remember, stoichiometry is the math in chemistry that requires a balanced chemical equation. The math in chemistry that requires a balanced chemical equation. Okay? The math in chemistry that requires a balanced chemical equation. So, I have a balanced chemical equation here. Back when we were in Unit 1, we learned how to set up a problem using the dimensional analysis process. So what would we do with this starting amount of 15.75 moles of methane using the dimensional analysis process?
Put it over 1.
Put it over 1. Okay? So this is our starting amount, 15.75 moles, and methane is a species. We're going to put that over 1. So 15.75 moles of methane goes over 1. All right? And now there's stoichiometry where you don't start with that, but that's most of it starts just like this, and it makes it a lot simpler to remember that. Now, if I were to look at the coefficients here, and we're looking for carbon dioxide here, what is the coefficient in front of the methane?
1.
Yeah, there's not one listed, but it is implied a 1. And the coefficient here is 2, and this is a 1, and that's a 2. Okay? Now we can think of that as being 1 molecule of methane, and 2 molecules of oxygen, 1 molecule of carbon dioxide, and 2 molecules of water. But if we multiply this 1 molecule of methane by 6.02 times 10 to the 23rd, how many will we have?
1.
Simple answer is a mole.
Oh, yeah, 1 mole.
Yeah, 1 mole. If I multiply this by that same number, Avogadro's number is what it's called, how many moles do I get?
2.
And this?
1 mole.
1 mole and 2 moles. Okay. It turns out that if we think of these as being moles, by multiplying the whole thing by the same thing, it doesn't really matter because it keeps everything equal anyway, we can make our math actually easier. The math is going to be complex enough, but this simplifies things an awful lot. So we're going to think of this as not 1 molecule, but 1 mole, which is 6.02 times 10 to the 23rd molecules. Okay? And this is going to be 2 moles, and 1 mole and 2 moles. Okay? All right. So in the problem, if we want to go from moles of methane we have here to moles of carbon dioxide, which is what we have here, we just need what's called a molar ratio. Now, when we built conversions earlier in the year, we always had to have an equality statement, right? And if this were a conversion unit, we would have to have an equality statement. But this is not going to be a conversion unit. It's a conversion factor, okay? And this conversion factor is a molar ratio. And it's just a ratio of moles. That's it. It's a molar ratio. Simple. Anytime you're going from one chemical species, like this methane, to another chemical species, like this carbon dioxide, you have to have a molar ratio. So what's the ratio of the number of moles of methane to the number of moles of carbon dioxide? What is the ratio? 1 to 1. Right. This isn't hard. 1 to 1. All right. So we need 1 mole of methane, and where would I put that in this conversion then? On the bottom, because I want to be able to cancel moles of methane that are here. So we're going to put our 1 mole of methane on the bottom. Okay. And we're using a ratio of moles here. We want to find carbon dioxide. So what do we put on the top? 1 mole of carbon dioxide. 1 mole of CO2. Okay. All right. What do I do to simplify this now? Cancel out. Moles cancel moles. Methane cancels methane. And I have moles of carbon dioxide. I'm ready to do the math. Well, this is pretty simple math, isn't it? This times this is 1. It's 15.75. Divided by 1 is 15.75. And so the answer we get is 15.75 moles of carbon dioxide. Pretty simple, huh?
Yeah. I heard it gets a lot harder.
Oh, it does. It does. It gets a great deal harder. All right.
Did that go beyond the scope of the class?
No, it's not beyond the scope of class. All right. That's where we're going to start, though. Look, anytime, just remember this now. This is the basic idea behind stoichiometry. Anytime you go from one chemical species to another, you've got to go through Moleville. You with me? Did y'all hear what I said? You got to go through Moleville. All right? You got to convert. You got to go from moles to moles. You cannot go from one chemical species to another chemical species using any other measurement unit except moles. You cannot go from one chemical species to another. You cannot convert from one chemical species to another without going through moles. And the molar ratio won't work without a balanced chemical equation. That's what stoichiometry is about. Okay, now it does get more complex, but that's where we're going to start. All right, so let's do this. If methane is burned in air, how many moles of water will we produce from that 15.75 moles of methane? So, given the example I just showed you, you can solve this problem, right?
Yes, sir, we can.
Please do so. I'm going to...
Don't have to plug anything in.
I got the answer.
All right, so here's the previous problem, okay? And with the previous problem, we're trying to find carbon dioxide, and we had 1 mole of carbon dioxide that we put right there. This time we're trying to find water. How many moles of water are there in the balanced equation? 2. So what do you think is going to change here? That's going to be 2 moles of water. And that's what I have here, 2 moles of water, and I get 31.50 moles of water. So now listen, here's the thing. You've got to be careful about significant digits. We learned about significant digits in Unit 1. I have 4 significant digits here, and these 2 numbers and this number here are all counting numbers, so those aren't used for significant digits. Only the measured and calculated numbers like this one are used. So we need 4 digits here. When you put this in a calculator, if you put it in a calculator, you're not going to get the 0. You're going to get 31.5. So you have to be smarter than your calculator. Okay? All right, now, listen carefully. This is the molar ratio part. This is the converting from one chemical species part, okay? The problem is we can't measure moles. So if we're going to actually use this stuff, we've got to be able to convert from something we can measure to moles. And for that we have what you did for homework, molar mass. Because one of the easiest things to do for measuring the amount of chemicals is to measure the mass. And then we can convert to moles, and that's what molar mass is for. This is a different problem. All right, so let's look at the problem again, okay? Just listen, please, Listen. Calm down. Thank you. You know I'm recording this, right? Your parents can hear me telling you to calm down. Calm down. I want to specifically call up Eva's mom and tell her to watch this video. Okay. Now, pay attention.
What about me?
Well, you don't need me to call your dad anymore. So. All right, here we go. All right, now look. But the starting of the process is the same. What do we do with that 15.75 grams of methane?
You gotta change it. Put it over 1.
Put it over 1. That's what we did before.
That's from up here.
No, it's not. There's a fire.
Now, here's the thing. Here's what I said a moment ago. To go from methane to this other species we want, okay, let's see, this problem was asking for, what was it, water or CO2? Water? Okay. To go from here to here, I've got to have moles. And I don't have moles. I've got grams. So that stuff you did for homework where you calculated molar mass, that's what this is all about. So we need to know the molar mass of methane. And since we did it for homework, you guys know how to calculate the molar mass. So calculate the molar mass for methane, please. All right, this should not be hard. I hope you've gotten it done already. Carbon has an atomic mass of 12.0107, yes? 12.0107. This number right here, from the periodic table. Average atomic mass. Okay. All right. So, and we've only got 1 carbon. And then we've got hydrogen, and hydrogen's atomic mass on the periodic table is 1.00794. And we've got 4 of those. We multiply that by 4, and we get 4.03176. I've lined up my digits very carefully so that I can see there's an empty slot here. So when I add these numbers together, and I get 16.04246, I can see this last digit over here results from an empty slot. And I'm going to underline it because we don't want to keep it. It's an insignificant digit. Draw an arrow to show that I'm rounding off. This is the only operator that's allowed to show that you're rounding off. And so our answer is going to be 16.0425. And here's what I want you to start doing now. From now on, from this point forward, this is the only way that you're allowed to calculate molar mass in this format. Okay? And so, but when you get to this, you got to have an equality statement. And the equality statement is going to work like this. This is grams of whatever the chemical is equal to 1 mole of the chemical. All right? So this process, this whole thing right here, this is the allowed method, the acceptable method. Okay, the only acceptable method for calculating molar mass in this class, okay? Everybody understand? Now then, now in Unit 1 we learned to use equality statements like this. In Unit 1 we learned to use equality statements like this. We said that this number needs to be put on the bottom here because it matches the units and species I have in the top of this fraction. So when I have grams of methane here, I need the side of the equality statement that has the matching units and species to be on the bottom of this fraction. And so we'll put 16.0425 grams of methane on the bottom. The other side of the equality statement goes on the top. 1 mole of methane goes on the top. And when we simplify by canceling out grams and methane, we're at moles. Okay? But the problem asks you for not the moles of methane, but moles of water. So all we got to do is build our molar ratio now from the balanced chemical equation. And so we've got 1 mole of methane here. And how many moles of water? 2 moles of water. Simplify. Okay. And we're ready to do the math. 15.75 times 2. Hit enter on your calculator. Then hit divide by and put in this number and enter again. So you multiply everything across the top as one operation. But when you divide by the stuff on the bottom, you have to enter and then divide. Enter and divide for everything that's on the bottom. Okay? Got it? All right. So do that math, please. Practice with your calculator while you have a chance. Guys, this is the unit where calculators are essential. And you need a standalone calculator, not the one on your cell phone, because that's the only kind you can use on a test. So if you should have a standalone calculator. You should have it here every day so that you can practice with it every day. So when the test comes around, you've got it. If you're using your cell phone or some other calculator now and a different calculator on the test, that's a lot of potential for mistakes. Okay, and I'm trying to help you guys make an A. All right? So please, bring your own personal standalone calculator to class every day. Chastity, did you hear me?
Yes.
What did I say?
I got that.
What did I say, Chastity?
Oh my God, this is better.
Yeah, Chastity, listen this time, okay?
Okay.
Bring your own personal standalone calculator to class every day. Okay? All right? Michelle, did you hear me that time?
I heard you this time.
What'd I say?
Bring your own personal calculator to class.
Well, y'all was there when I
Some people heard it. Good. All right.
Bring your own calculator.
All right. So, Brittany, what is the answer?
It's a number.
Brittany, where's your calculator? Come on.
It's in my book bag. I got it.
Get your calculator out of your book bag, girl. Get it out.
I got
Get it out. No, I don't want you to answer it, okay? Zakiah, what's the answer?
What?
I can't hear you. Speak up.
I heard that.
I know. So fake
Leave it alone.
For real.
She's so quiet. We can't hear her. All right. What? Really? Then you didn't do it right in your calculator. Now, you might not have gotten as many digits, and that's okay. If your calculator only goes to this many digits, that's okay. You can write down every digit your calculator shows. Carol, you hear me? All right. Now, how many significant digits do we need in this answer?
4.
4. With multiplication and division, the rules are you take the measured or calculated number, these are the only two that are measured or calculated, and find the one with the least digits, and you have the same number of digits in the final answer. So starting from the left, 1, 2, 3, 4, those are the digits we're going to keep. Going to underline everything else. The units we have left are moles and H2O. We're going to round it off and get rid of those, or round off those digits, because that's going to make this 3 a 4 here on the end. So 1.964 moles of H2O. Okay, that's our correct answer for this particular problem. For some reason, this is not wanting to advance. Okay. All right. All right, well, let's try this problem then. Okay? Here we go. If methane is burned in air, how many moles of water we produced? From 15.75 grams of oxygen. Different problem. No, we did not just do this.
You look like a banana.
So this time we're starting with oxygen. 15.75 grams of oxygen. The molar mass of oxygen, there's two oxygens in an oxygen molecule because the oxygen we work with is O2. Okay? And that gives us a molar mass of 31.9988 grams of O2 equals 1 mole of O2. And we build our conversion unit from that. 31.9988 goes on the bottom. Grams of oxygen go on the bottom. Moles go on the top. And when we do the math, we get 0.4922 moles of H2O. Okay? No?
No.
What's the matter?
That's what I got. I hope you do mold.
What?
No mold.
I got you. All right, here we go.
Hold on. Oh,
All right. So we got to stay focused and stay on task. Okay? It's good to have fun, but not at the expense of getting the work done. Okay? All right. Here's the next problem. Now notice there is a difference. Be careful about the difference. Okay? Do you see the difference?
yeah. Wait, no.
How many grams?
It's a methane.
Was
Yes.
that it?
That's it.
Was that it?
I got it first. Oh, yeah.
Okay? All right. So the difference here is we're trying to find grams of water. So in the previous problem, we went from grams of methane, which we're doing now. Well, actually, 2 problems ago. We started with grams. So the problem's going to start exactly the same way. The only thing, you're ending up in a different place. Okay? So read the question carefully. Make sure you're solving what it's asking for. This is the problem we did previously, okay? We already found the moles of H2O. And this new problem is only trying to find the mass of H2O. It's the same problem except that we got to go another step. You with me?
Yeah.
So everything we did for this problem, you got to do for the new problem. So here is where we are then in this problem. Now I went ahead and put back in the atom inventory here because you need to remember that when you do a homework problem, which I will assign in a minute, you've got to have an atom inventory when you balance an equation. Okay? You've got to show me the molar mass when you do the molar mass, molar mass ratio here. Okay? So we've gotten this far, and it's always a good idea to cancel as you go, and that should be CH4 on the bottom there. For some unknown reason, I put water there. So let me change that out here to CH4. I'll fix that and make it a little neater here in a minute. Okay, so the next thing we need to do is to get from moles of water to grams of water. And somebody said reverse engineer. Kind of, yeah, it is kind of reverse engineering because you still need this kind of calculation. For water, we went from grams to moles using this. Now we're going to go from moles to grams. Okay? So what we need to do is to write out a molar mass calculation for water.
18.0153.
Yeah, but it's going to round off to 18.0153. You're right. Let's do this. 1.00794 times 2, because there's 2 hydrogens in water. 2.01588. Guys, you really need to pay attention up here. You really need to pay attention here. 15.9994 times 1. There's only one of those, so it's going to stay the same. We have an empty slot here under this 8. When we add them together, we get the number that AJ was talking about, 18. And we've got to round off that last digit because of that empty slot that's right here. Okay? And so we are going to get 18.0153. And now this is going to be the basis for a new conversion unit here. Okay? So I have moles of water on the top. I want moles of water on the bottom. And the 18.0153 goes in the top. We want to simplify by canceling out moles and water. And we do the math. And I got 35.3736605891. Units I have left are grams and water. I want how many significant digits in the answer? Yeah, because there's 4 here. Of the measured and calculated numbers, this one, and this one. This one has the least digits. That's 4. So we want 4 in our final answer. I go on everything after the first 4 digits and round it off. And we get 35.37 grams of water. Okay? And you may notice that I turn my paper sideways here to get all that in there. You may not need to, but if you write large, it might be helpful. Okay, you take 15.75. You can skip the 1 because that just gives you the same number, right? Times 2 times this number. Hit equals. Hold on. And then you divide by 16.0425. This way. Alright, so 15.75. Please be quiet and listen. Times 2 times 18.0153 and hit enter. And then I'm going to divide by 16.0425. And I get the number I just gave you. Well, it's always helpful to do the math in your calculator twice. Okay? Once may not be enough. Alright? So this is the homework problem I want you to solve. If it were me and I was trying to do well in chemistry, I'd do that as soon as possible rather than wait till like Sunday night if you got a weekend after you've had a chance for it to go stale on your head. But if you practice earlier, it's better than practicing later. Okay? Now, you do have the notes. I will be recording this and putting it on YouTube so you can go back and review. But it's probably better for you to do the math early rather than later. Now,